This is Mr. Schwanke. We're going to continue our studies of vibrations and waves that we started before our little health adventure. And they're actually kind of cool to study because they're all around us. Sound waves and light waves and electromagnetic waves when your cell phone is being used, and we have a lot of waves in our world. Okay, ocean waves are what we probably think of, and that's the picture you see here. I tried surfing one time and it wasn't pretty, so I don't go out on waves like that. And we'll look at a movie about this, which is called the Verrazano Narrows Bridge, which was in Washington State, and it sort of blew down in some windy weather. Okay, we have pendulum clocks in our homes and in some office buildings and things. And pendulum clock has weights, usually 3 of them, and a big pendulum that swings back and forth. Pendulum can be a small little weight on the bottom of this pendulum or something big. This one looks like a plate or something, but basically take the mass of that pendulum, mass of that object, and concentrate it at the center, and you could put that weight right there, and it wouldn't have to be so big. Okay, and we also know the pendulum swings back and forth, and that back and forth motion is what gives the clock a time reference in order to keep time. These don't work very well on ships, so it was a whole other adventure to try to get a clock that would work on a ship where it was rolling and pitching. And someday there's a couple of good videos on that about how they finally overcame that. Okay, when this thing is hanging straight down, then the force pulling down on the pendulum is the weight of that object. When you pull it up and down, some of the weight is still pulling straight down, but some of the weight is trying to make it go back down toward the center, like a kid on a swing. Put a kid on a swing and push her way up high and then let go. You can see that she's going to swing past the bottom and go past that to the other side, and so on. So this motion is called simple harmonic motion. Harmonic because it repeats itself, and we talk about objects at equilibrium. The kid at the bottom of the swing would be in equilibrium. The kid at the top would be the position of maximum energy and maximum displacement from the equilibrium. We had a lab that we were going to do with the Logger Pros where we take a weight and pull it down, and we attach it to springs. If you remember, I had a box of springs in the classroom at different intensities. We express the intensity of a spring by something called the spring constant, which is a number that tells me how many newtons of force I have to use to stretch out the spring a meter. Well, we're not usually going to stretch out a spring a whole meter, so we'll take 1/100th of that or something and say how many hundredths of a newton does it take to stretch it a centimeter. Anyway, it's a force per length, and that we call that the spring constant. And if we pull this spring, if we have this spring in a neutral position, then right here, it's just the spring itself. If we put a weight on that, it'll pull it down to some position. If we put twice the weight on that, the position will be twice as far, as long as we don't overstretch the spring. So that's describing a couple things that you worked on in our lab last week. The period of harmonic motion is the period for a complete cycle. So if I pulled this thing down and it went up and back down again, that would be the period of the motion. Or I could do it the other way. I could pull it up and let it go back down. Period is the time needed to go one complete cycle, and amplitude is how big it is displaced from its position where it would like to be if we weren't messing with it. So the amplitude of this guy is 2x meters. The amplitude of this motion, look at the top of it, is x meters, and there's no displacement for this guy. And so we see that the force exerted by a spring is directly proportional to the distance that it's stretched. So they're kind of handy little devices for shutting screen doors and making electronic and mechanical devices work. This guy named Hooke, who wasn't a very pleasant guy, and he was not one of Isaac Newton's friends, but he had a law that said force on the spring is proportional or equal to kx. K is a constant, so if we put a k in there, a constant, we can have an equal sign. If not, then we have to put one of those little proportional to signs. But basically, the force is in the opposite direction of how the string stretches, and that's called Hooke's law. And if you have a Regents test this year, you will have some Hooke's Law problems on there, I guarantee it, and they're not hard. Given a force, which would be weight force, the force is the weight of this object, and x is how far it stretches out. The force has to be in newtons, and the stretch out has to be in meters. So if it was 50 centimeters, it'd be 0.5 centimeters. So anyway, we'll look at a Hooke's Law problem in a minute. And another thing that's kind of interesting, if we stretch out a spring and don't stretch it too far, since it's a proportionality, it's just directly linear. So the force that we stretch it out is proportional to the distance that it goes. So if I go up 1 block, then it goes over 1 block, make the force be twice that much, goes over 2 blocks, make the twice be 4 times that much, goes over 4 blocks on each side. So that's directly proportional. And we have another kind of energy that we look at. It sort of looks like kinetic energy, but it's the spring energy that I'm putting into that spring when I stretch it out or compress it. And that's going to be basically 1/2 kx squared. K is spring constant in newtons per meter, and 1/2 is just basically 1/2 of this area is shaded in, is where that 1/2 comes from, and x is the distance that it's pulled out, and k is the spring constant. Okay, so harmonic motion then, SHM, would be simple harmonic motion, and it just oscillates back and forth, but there's air friction and there's friction in the spring, so the motion eventually decreases. But if you look at it on a graph, it looks like a nice sinusoidal graph, and I wanted to do that lab, but if I can think of a way to do it and show you guys on the video, I will, but it's going to be a little hard since I'm not supposed to go back in the building. Okay, here they put a bag of potatoes, which has a weight of 56 newtons, and what do they give us? They give us 56 newtons, and it stretches by 18 centimeters. So when Hooke's Law, F equals kx, well, F is the force, that's going to be the 56 newtons, k is the spring constant that we don't know, and x is the distance in meters that it stretched out. It stretched out 0.18 meters because it was 18 centimeters, 56 newtons. I had to rearrange this equation to get k here, and then we can solve k as 310 newtons per meter, which is pretty strong spring. And then if I want the spring potential energy, I just plug those numbers into the 1/2 kx squared, and 1/2 k is 310 newtons per meter because we figured that out, and x was 0.18 meter, and we square that. And any kind of energy is expressed in joules. So that's a simple harmonic oscillation problem. You can hang around with potatoes if you want to. Okay, now to solve a pendulum problem precisely is a little bit hard in terms of because we have one force that's constantly varying with the angle of the pendulum. We always have the weight force straight down, and the weight force doesn't change, but part of the net force on this thing is going to be the pull of the string holding it up, and the pull of gravity, the part of gravity that makes it want to go down. So if you want to do a full-blown pendulum problem, we have to use calculus, which we won't do right now, but as long as the angle that you stretch it out at is less than about 10 degrees, you can sort of not worry about this one in terms of calculations. But there is a tension force in this string or wire, whatever's holding that thing, and there's the force of gravity, and there's part of the gravity force that's trying to make it go back to the equilibrium position. Okay, there's a formula for the period of pendulum, which is in your formulas on the equation sheet. T, capital T, is the symbol for period of time, and 2 pi 1/g. So this shows us that the 2 pi is telling me there's some kind of periodic motion, which we know. L is the length of the pendulum, and g is the gravity that it is exposed to. On the Earth, that would be the same everywhere, but if we took the pendulum to the moon and we knew the length of the string, we could figure out the gravity of the moon that way. Okay, T in periods of seconds for a complete cycle. L is the length of string in meters, and gravity on the Earth is 9.81, but it could be differently someplace else. Okay, here's a problem like that. It says a pendulum has a length 36.9 centimeters, period 1.22 seconds. What's the gravity acceleration? So what do we know? Length is 36.9, which is 0.369 meters. We know the period is going to be 1.22 seconds because it gave us that, and we want g. take this guy and do a little bit of algebra, which you gotta be careful with here, and solve it for g. You're gonna have to square both sides to get rid of this stuff. And you get an expression g equals 2 pi squared L over t squared. Plug in all the numbers and you get an answer of 9.78 meters per second squared. Well, that's not the real value for gravity, but gravity does vary. Gravity is stronger at the North Pole and less at the equator, because at the equator, the world is stretched out a little bit. It's oblate, it's fat in the middle, and at the equator, you're actually sunk a little bit toward the center of the Earth. Okay, so we got an answer there in meters per second squared, which is close to the gravity constant, and that makes you confident that your answer is probably correct. Okay, resonance is something that occurs when a small force is applied at regular intervals. So if you push a kid on a swing, there's one particular time you can push the kid and make him or her go faster. If you try to push the kid when the kid's coming up toward you, it's going to knock you over. So resonance include rocking a car to free it from snowbank and jumping on a trampoline or diving board. And resonance can cause problems. If you have a bleacher and you have 500 high school kids stomping in a basketball game, you can have a situation where the bleacher would collapse, and that's not good. Audiences in theater balconies, for instance, can damage it, and if we have troops marching over a bridge, they're not supposed to all stay in step, because that can make the stress on the bridge much greater. I'll show you a video on resonance after this PowerPoint on the one on the Verrazano Narrow Bridge. Here's a picture of this bridge, and something doesn't look right on that bridge if you look at it. It's like curved there. And when you see the video, you'll see the whole bridge was just flopping back and forth in the wind, and the wind and the bridge width were just like right, so that the resonant frequency of the vibration corresponded to a certain kind of wind that that bridge got, and it got it. And we'll see what happens when we watch the video. Okay, let's see. Mechanical waves, you looked at waves when you did that lab last week. Water waves, sound waves, and the waves that travel down a rope or spring are mechanical waves. They require something we call a medium, stuff to go through, water or air or rope or spring. Other waves can't be directly observed, like sound waves, so we use mechanical waves as a model. Two basic types: a longitudinal wave, where the energy goes along the direction that the spring is stretched out where the thing is traveling, and transverse wave, where the motion of the wave is perpendicular to the direction it's traveling in. Transverse wave, if I have a rope and I push it down and then I shake my hand back and forth, I'm going to produce waves that travel outward from my source and down initially and then up initially. So that's a transverse wave, and the direction of the wave is perpendicular to the direction that the medium moves, perpendicular to the direction that the wave moves. And it looks like a letter T, and you can think of that one as transverse. So we can do a pulse, which would be a single bump, or we can do back and forth pulses. And again, you played with that little string thing last week in the lab, and you were able to make some waves. A longitudinal wave, if we have a big slinky in the classroom, if we ever get back, we can play with it, but if we pinch part of the slinky, then that pinch will spread out in two different directions from you, where you are, traveling in the direction of the wave. It's a compression in the spring that travels along. And that type of compression is sort of like a sound wave, where when you talk, you compress the air, and that pulse travels to the ears of the people next to you, and they can hear what you said. Longitudinal wave then goes along the spring, or goes along the direction of the medium is in the same direction as the wave is moving. Ocean waves are kind of a complicated thing. That when ocean waves goes across, it looks like the water is actually moving, but if you put a reference point like a cork or a bird or something like this, as the wave comes, the object just goes, let's say this wave is coming from here, so this object starts to go up, and then as the wave is coming, say the wave is coming this way, so the object goes up, hits the highest point, goes back down, and finds itself back in the trough. A trough is the low point of a wave, crest is the high point. I guess I had the motion backwards then. So ocean waves are not moving the water, it's energy moving through the water, except when they break on the shoreline, and there the top of the wave surges toward the shore and brings water ashore. But deep ocean waves are just energy traveling through the water, and it's a very efficient way to travel energy. It can travel thousands of miles. That's a surface wave. Surface wave can also exist underwater, where you have cold water and then warmer water on top of it, and that's a gravity wave. Navy worries about those with submarines, because a gravity wave can be 20 or 30 meters in wavelength and have an amplitude of several meters, and it can make the whole submarine go up and down rather quickly. And there's no real way to predict them. So gravity waves they're called slicks because they make an impression at the surface that there's something going on down below. Okay, speed of a wave. Well, speed is defined as distance divided by time, delta d over delta t. So we take the same thing for a wave. And the speed of the wave depends only on the medium through which the waves move. Basically, waves move faster in denser materials. In the air, sound travels about 330 meters per second, depends on temperature. In a piece of steel, sound travels over 1,000 meters per second. So if a train is coming down a train track and you are dumb enough to put your ear on the track, you can hear the train when it's much farther away with the sound traveling through the track as opposed to sound traveling through the air. But don't try that at home. So the speed of the wave is the distance or the rate at which it moves down the medium, whatever that medium is. Amplitude is how big the pulse is. Amplitude is the maximum displacement of the wave from its position of equilibrium, where it would be if it wasn't. So if you have a lake that's still and then you get a thunderstorm and you get some waves on it, well, if the wave is 1 foot above the still water point, that's the amplitude, although it'll look like if you have that next to a deeper point, it look like it's 2 feet because you'll have on the other side of that wave will be the trough and the water will be 1 foot below the equilibrium position. But the amplitude is the displacement from the position of rest to where you see the highest point. Waves' amplitude depends on how it's generated, but not its speed. Waves with greater amplitudes transfer more energy. That kind of makes sense. If the water's piled up higher, it has more energy moving along with it. Here's a picture. This is a wave. The wavelength is the distance from there to there. That little symbol is wavelength. We could also go the distance from this trough over to this trough. That would count. That would be no problem. And amplitude is this little distance from the rest position to the high point. Crests are spaced by 1 wavelength. And troughs are spaced by 1 wavelength. And the lambda symbol represents wavelength. Phase is what the wave is doing at that point in time. Maybe all the particles on the wave are going up right now for a particular wave, but there may be a wave nearby where all the particles at that point are going down. And we can have 2 waves intersecting each other, and we call that basically combination waves. Okay, wave speed and amplitude can describe both pulses and periodic waves. Period and frequency apply only to periodic wave. Period of a simple harmonic oscillator, such as a pendulum, is the time it takes it to do 1 complete cycle. We learned that when talking about the swing. Frequency is 1 over period, which makes sense. If you go stand in the water at the beach and every 4 seconds a wave splashes across your feet, then you're getting 1/4 of a wave every second, because it takes 4 seconds to get a whole wave. So frequency and period are reciprocal to each other. The word for frequency is hertz. It's not named after a car rental company. It's named after a German scientist who studied wave motion several hundred years ago. A hertz is 1 operation or 1 oscillation per second. Frequency and period of a wave are related by that. Frequency 1 over period. These equations are all on your equation sheet. Wavelength of a wave is the speed multiplied by the period. So the velocity of the wave multiplied by the period is going to give me a lambda, the wavelength. That's not a very good lambda. And we can also then solve lambda is, since this period is 1 over frequency, we can, instead of writing t here, we can write 1 over frequency, so we can get wavelength this way too. Lambda equals velocity divided by frequency. And these equations are useful because sometimes you're given 2 of the 3 things, but again, I think these are mostly in the equation sheet. When you have a boundary between 2 different mediums, some things can happen. Part of the energy here in this spring will bounce back. If I send a pulse down this way, part will bounce back and part will get through. So this pulse here, the black pulse, was coming to the right. Some of it traveled through this thing and got into the silver spring, but a little piece of it got reflected back. So that's, if you have a boundary between 2 surfaces, between 2 mediums, you can get some funny things going on. There you see the two separating. And wave reflection, I can send the wave down to a fixed point, and it'll bounce off that fixed point and come back upside down. Again, you guys are playing with that little simulation last week. If it does that, then we call the wave inverted, if it's at a fixed point. Okay, superposition of waves is a fancy term to say that two waves are in the same place at the same time, which can happen, especially if they're moving through each other. Principle of superposition says that displacement of a medium caused by two or more waves is the algebraic sum of the displacements caused by the individual waves. And we can get interference. At sea, I remember we had called a rogue wave on our aircraft carrier. And a rogue wave is where two waves combine, and the crests happen to combine at just the right time. So you might have a 30-foot wave and a 40-foot wave coming at each other at a slight angle to each other. And as they pass through each other, you could get a wave of 70 feet. It just kind of rises out of the ocean and is there for a few seconds, and then it goes back down again. And you don't like those if you're in a boat. They can cause some problems, even if you don't like, even in an aircraft carrier. We had water wash over the flight deck of our aircraft carrier, which was 80 feet above sea level. So the wave we encountered was over 80 feet tall. Didn't sink us, but it woke us all up. It was the middle of the night. Okay, here's some pictures of superposition waves, and they're showing you this wave is moving to the right, this wave is moving to the left. As they get closer to each other, they look like this. As they get through each other, the up part of one wave cancels the up part of the other wave, so it actually goes flat for a second. You don't see a wave there, although the waves are there. They're just canceling each other, and then they pass through each other. So this wave here looks just like it did over there, and this one here looks like it did there, and they keep traveling. We can also have two waves make a bigger wave. This is where you can get in danger on a ship. Big wave here, makes a really big wave here, and it's twice the amplitude of the individual waves, and then it goes back down again. That can be dangerous. And here we have small waves that can cancel out and make almost nothing as they travel through. So superposition waves are interesting, and there's usually a test question on those in our regions. Okay, let's see if I can find the applet for the bridge thing. Verrazzano-Narrows Bridge. Let's see here. We don't want to do this we're going to do a pendulum. We'll go to search it. Okay, Verrazzano-Narrows Bridge. Let's try a video. I guess we don't get sound on this one. It's in, there's a new one now. Okay, and it's Long Bridge. It was, there it's full of people. And let's make this be big screen here. Okay, the first bridge was a little wooden one, and a designer built one. And we can see that's the new one, but this was I want to see when it actually starts to rock and roll. Let's move ahead here. This isn't a very good video. Let's try something else. That's a different bridge. Let's see. Next time I'll make this link part of the PowerPoint. I'll have to put this on the PowerPoint that we do next because I want to find one that has sound and we can see it moving. That's it. Please look at the assignments that are listed on our daily sheet. When you look at our sheets, they look complicated. Just look at the particular day that we have in question. So today's thing talks about this video on sounds, on waves, and vibrations and waves, and there's a couple things to do, and then don't worry about anything else. If you don't know how to submit things that I'm asking you to submit, go to the thing that's linked from the main page which says how do I online, and it was written for the biology kids, so I think you guys probably know that, but it does show you how to send me a paper so I can check things. I have to have grades this time, and you're going to take a picture of the paper with your camera and send it to me just as an attachment to an email. If you don't know how to do email attachments, look at item 6 on the online thing. And we'll talk about these tomorrow when I go through some more things. Have a good day and take care of yourselves.